we discussed how to identify the crystal directions, and then we started to discuss to draw the crystal plans. So I think we discussed these plans 100 001. So it's a simple plans, and I remember I gave these questions, these 6 questions. Am I right? Am I right? Say yes or no. I think I gave these 6 plans to draw. Dear students, yes, okay. So, did you try this? Did you try this answer for this? So, I'm going to discuss now. So, you better check on my answers with your answers. So, first plan is bar 101. Bar 101. So, how to draw this plan? Bar 101. If you have bar 101, so you need to find out the reciprocal of this. 1 over bar 1, 1 over 0, 1 over 1. So bar 1, infinitive 1. So yx is infinitive, x is minus 1, z is 1. So if you found this minus 1, you have to change the origin. Now the origin is here, but you have to change the origin into here, because you are having minus 1. So your origin is here, now here. So minus 1, so minus 1, y is infinitive, and this one, z is 1. So the plan is there like this. This is your bar 101. Okay, do you have any doubt with this? Now we need to find 1 bar 1 0. So 1 over 1, 1 over bar 1, 1 over 0. So 1 bar 1 infinitive. 1 bar 1 infinitive. So you are having minus 1 at the y-axis. So you have to change the origin. So you have to change the origin is here. So plus 1 minus 1. And x is plus 1. And z is infinitive. So here. So this is your plan. Now, okay. So this is 1 bar 1 0. And the third one 1 2 0. 1 2 0 means 1 over 1. You need to find the reciprocal. 1 over 2, 1 over 0. So 1 half infinitive. So x is 1, y is half, then z is infinitive. So you need to draw this way. And here also. Then this is your plan. It should be parallel to y-axis. Parallel to y-axis. Sorry. So this is your plan. Okay. Do you have any doubt with this? If you have any doubt, you can send me a message. If you want more explanation, you can send me a message to me in the chat box so that I can explain more. You have any doubt with this? Okay, no more questions. So I'll move to the next. Other one, 112. So 112 means 1 half. Reciprocal 1 half. So this is 1, this is 1, and this is half. There is no change. So here it is your plan. One half. 1 How to draw 1 So 1 means here 1 1 1. So 1 1 1 1 1 1. Then bar 1 1 1. Bar 1 1 1. So bar 1. So you have to change the axis. So this is you have to make this is your origin. So bar 1 minus 1 and 1 1. How to draw this way? It's little bit different. Let me color this. So this is your plan. Okay. So I think you all have understood well. So please check my answers with your answers. Now you need to draw bar 1, 1 bar 1, 1 1 bar 1, 1 bar 1, 2. So we will discuss this as well. So first we will draw this. Bar 1, 1 bar 1. So you have to change the axis. But you have here 3 bar 1, 1 bar 1. So you have to change the axis for x direction and also z direction. So this is, if you take this is positive, but you need negative. So we will take this as our origin. So minus 1 is here and plus 1 and plus axis. So this is minus axis. So this is your axis. That is this bar 1, 1 bar 1. So this is your plan. Do you understand what I am saying? So here there are two minus. So you have to select the suitable origin. So this point is here plus x. Sorry, this is plus x. This is minus x, and this is plus y, and this is z plus z. So the opposite is minus z. This is your axis. This is your origin. Similarly, the second one, bar 1, 1 minus 1. Sorry, 1, 1, bar 1. 1, 1, bar 1. So here at this time you have negative z. So you will take this as origin. So x is plus 1, y is plus 1, z is minus 1. So 1, 1, bar 1. So this is your plan. These are something different plans. This is your plan. Other one, 1 bar 1, 2. 1 bar 1, 2. Dear students, are you taking the notes? I don't have notes for this. You have, it is your duty to take the notes. It is you are the responsible person. You have to draw these diagrams. 1 bar 1, 2. So 1 bar 1, 2 means 1 bar 1 half, reciprocal of this plan. 1 bar 1 half. 1 bar 1 half. So this is 1, but here you have bar 1. So you have to change, the origin is here. So 1, this is plus 1, this is minus 1, and here half. Your plan. 1 minus 1 half. So that's all for drawing the plans. So don't forget to find out the reciprocal of these plans. That is very important. So you must know how to draw the directions as well as how to draw the plans. So these are the some plans we already discussed: 100, 110, 200. And here are some examples of plans. So you can uh, read it and go through it. These are also some examples of plans. Plans in lattices and Miller indices. So these are known as parallel plans. Here you can see 010 plan, 010 plan. So these are the parallel plans with same Miller indices. Here 1 bar 1 0, 1 bar 1 0. So these are also parallel plans with same Miller indices. See, these are also parallel plans. 010 plan, this is 020 plans. Very similar, but see the difference between those two plans. Here 010, so the difference is 1. Here 020, so the difference between two plans is half. So these are known as set of parallel plans. Now we will find out the distance between two parallel plans. Here you know that there are plans. So you need to find out the distance between two parallel plans for this distance between two parallel plans. See here you can see this diagram. This is a plan. This plan is known as ABC. So this plan is known as ABC. So the plan ABC cut at point A axis, B axis and C axis. So the cutting point is at the A axis, that is PA, at the B axis, that is QB, and at the C axis, that is RC. These are the cutting points. So we will consider the expression for an interplanar spacing mainly depends on the type of crystal system. The type of crystal system means we studied so many types of systems. I think 7 Bravis crystal systems. So consider crystal lattice space of orthogonal axes. Orthogonal axis mean here these A, B, C are orthogonal axes and this is orthogonal. Here, this is orthogonal. If alpha, beta and gamma are the direction cosine of the normal, alpha, beta and gamma. See here, this is alpha, this is beta, this is gamma, this is your orthogonal. So, the alpha is the orthogonal angle from A axis and beta is orthogonal angle from B axis and gamma is orthogonal angle from C axis. So, DHKL can be written as PA cos alpha, PA cos alpha and QB cos beta, RC cos gamma. RC cos gamma, this is your DHKL. That means this distance is D, this distance is D, this orthogonal distance. So, PA cos alpha, QB cos beta or RC cos gamma. In mathematics, for the orthogonal axis, you can write this cos squared alpha plus cos squared beta plus cos squared gamma, that is equal to 1. So, you have to find this. So, cos squared alpha, that is equal to D squared over PA squared. Cos squared beta, that is D squared over QB squared. Cos squared gamma, that is also D squared over RC squared. So, you have to apply for this equation. Then, if HKL are the Miller indices of the plan ABC, HKL are the Miller indices of the plan ABC, H is equal to N over P, K is equal N over Q, L is equal N over R. So, this already we derived the Miller indices section. So, now you are going to apply these three into here. So, when you are applying, you will get this. DHKL, N is equal, N into H squared over A squared, K squared over B squared, plus L squared over C squared to the power of minus half. So, N is equal to 1. N is equal to 1. The minimum value of N is equal to 1. So, if you take N is equal to 1, you will get this formula. And for a cubic, A is equal, B is equal, C. A is equal, B is equal, C. So, that's why for a cubic, the equation, the interplanar spacing is equal to A over H squared plus K squared plus L squared. A over H squared plus K squared plus L squared. Okay, do you have any doubt for this? You have to work out here. Actually, you have to work out. I mean, from this point to this point, you have to apply and you have to simplify this formula and then you will get this formula. Now we will see that interplanar spacing. Here, D010, D010, D020, D010, D020. So, 0, H is 0, K is 1, L is 0. So, you have to apply A over H squared plus K squared plus L squared square root of. That is the interplanar spacing. So, you will get A here. Similarly, 0, 2, 0, A over 0 squared plus 2 squared plus 0 squared. So, A over 0 plus 4 plus 0. So, A by 2. If you want to find out, this is, you can say 0, 1, 0 plan. 0, 1, 0 plan. For example, this is 0, 2, 0 plan. So, if you want to find out the distance between these two plans, you have to subtract from D100 minus D020. Or else if you want to find out the distance between D010 plant, that is A. Distance between D010 plants, so that is A. Distance between 020 plants, 02 plants is, that is A by 2. Here you can see from the diagram, distance between 010 plants, that is A. Distance between 020 plants, that is A by 2. So by using this formula, you can easily find out the distance between two parallel plants. So here they gave an example. Estimate the separations between 100 plants and 111 plants in a cubic crystal. Estimate the separations between 100 plants and 111 plants. So 100 plant, it is obviously A over 1 squared plus 0 squared plus 0 squared, that is A. And 111 A over 1 squared plus 1 squared plus 1 squared, so A over root 3. So the A is the separation between 100 plant, and A over root 3 is the separation between 111 plants. Do you have any doubts? Dear students, please, you have to talk. Okay, that is the end of these crystal directions and crystal plans. I have some numerical questions, so I will discuss in the tutorial discussion part. Did you find the notes? Did you find the notes? I think I shared via the WhatsApp group, so that is easy for me. So please do check the WhatsApp group and access the notes. Thank you. Only one person responding for my questions. Others, I don't know what they are doing. Please have an interest on this subject. Okay, now we'll move to the another part, that is crystal diffraction. Okay, crystal diffraction. What is the meaning of diffraction? Have you studied physical optics and optical instruments section? Dear students, you have to open your mouth and you have to talk. Okay, so what is diffraction? Otherwise, I will call the person. It's better to call the person. BS 66. BS 66. BS 66. BS 66. BS 66. BS 66, unmute your microphone and talk to me.
Yes, ma'am.
Okay, what is diffraction? Did you study?
Diffraction means,
Oh, yeah.
yes, ma'am.
Yeah.
Spreading out of phase.
Sorry.
Spreading out of phase.
Spreading out of wave.
Yes,
Oh,
they pass through an aperture.
okay. Okay. So, whenever a light or any wave pass through an aperture, what will happen? That is diffracted. that is diffracted, and at the screen you can see the interference or diffraction patterns. There are two types, single slit diffraction or otherwise double slit diffraction. So at this stage there are two sources. So here then here also spreading, here also spreading. So there is a interference pattern also you can observe from this two slit or double slit diffraction. So here the important point is the aperture or obstacle. So the distance is d. The distance is d. So this distance should be equal to the lambda, wavelength of light. Then only you can see the interference or diffraction pattern. Otherwise, it is you can't see, because this condition should be satisfied to observe the diffraction pattern. So that is important concept or important theory for this diffraction. So this you have studied in your course of physical optics and optical instruments. But here we are going to consider crystal diffraction. What is the meaning of crystal diffraction? Crystal diffraction means we are going to observe a diffraction pattern by using a crystal. So here the slits are the aperture or slits are the obstacle we are using. But in the crystal diffraction, you have to use the crystal. You know that crystal has number of atoms. So crystal have number of atoms, whether it can be periodic or non-periodic. But if it is a periodic, you can easily observe. So here you can observe number of atoms. So when you direct a light source which is equal to interatomic spacing between two atoms, which is equal to interatomic spacing between two atoms, this space is act like a aperture or obstacle, and you can observe the diffraction pattern by using this crystal. So for example, if you direct a light or X-ray light here, because of this distance between two atoms, you can observe some diffraction or interference pattern. By using the diffraction and interference pattern, you can explain the structure of the particular crystal, you can explain the atomic length of the particular crystal, and some more information and the defects positions and also position of the atoms. So there are so many information we can gather from this diffraction pattern. So this crystal diffraction is very useful to identify and analyze the type of crystal and the information about the crystal. So that is why we are using this phenomena, crystal diffraction. Mainly crystal diffraction is useful in the research studies. So I'm going to cover the fundamental elements of crystal diffraction from this chapter. So first let's see some interaction. To explore the information about a crystal structure and its properties, the diffraction pattern produced by the crystal is being used as a crucial tool. It is assumed that the crystal might be regarded as a three-dimensional diffraction grating. So it is very important. In our laboratory, we are using some gratings, that is two-dimensional gratings. But here we are considering that crystal as a three-dimensional grating or aperture. Yes, any problem?
Slide not changing now.
Okay, wait. Uh, Can you see now?
Yes, ma'am.
Now the title is Determination of Crystal Structure.
Yes, ma'am.
Okay. Thank you for telling me about this. Okay. So the crystal are considered as a three-dimensional diffraction grating for energetic electromagnetic waves. Here, we are using mostly high energetic waves because the wavelength should be equal to interatomic spacing between two atoms. So that's why that is mostly the atomic spacing is angstrom. So atomic scale is mostly angstrom. So that is suitable for only X-rays because the radiation of wavelength less than or equal to 1 angstrom. So the wavelength that is 1 angstrom wavelength is suitable for only X-rays. So that's why mostly in the crystal diffraction we are using X-rays. To obtain diffraction pattern by a crystal, the radiation used for should have the wavelength comparable to the interatomic spacing distance. So the radiation wavelength less than equal to 1 angstrom would produce a successful diffraction pattern by those crystals. This condition should be satisfied in order to observe the perfect diffraction pattern. So the energy characterized by 1 angstrom. So 1 angstrom energy that is equal to 12.3 is equal to h mu, that is famous Einstein equation, that is equal to hc over lambda. So by using that lambda, you can find out the energy of that particular wave is 12.3 into 10 to the power 3 electron volt. So the energy characterized by this above radiation is X-ray. So this energy is matching with the X-rays. This energy is matching with the X-rays. So that's why mostly we are using the X-rays. Or else wavelength is matching with the X-rays. That is why we are using the X-rays. Electron beams as well as slow neutron beams wavelength less than equal to 1 angstrom are also employed to study the structure of the crystal, especially surface of the solid. So electron beams also can be useful as well as slow neutron beams. Electron beams also can be used to identify the information about the crystal. The diffraction of X-ray by crystals. So to identify the diffraction of X-rays, you should have one assumption, that is ions do not vibrate about their equilibrium position, because inside the crystal there are number of atoms. In natural, these atoms are vibrating themselves. There is a slight vibration. There is a slight vibration inside the atoms. So there's a vibration themselves. So that if you consider that vibration, you cannot find out the perfect diffraction pattern, because of the vibration there may some changes in the diffraction pattern. So that's why here we are assuming that ions do not vibrate about their equilibrium position. So we are neglecting that vibration, the personal vibration for the atoms or ions. So first we are neglecting, or we are assuming that the atoms or ions do not vibrate about their equilibrium positions. Normally they are slightly vibrating. I think I discussed in the course of oscillation and AC theory. Am I right? I think so. So this is your assumption. So the distribution of intensity of the scattered X-ray reveals the location of ions within the sample. the distribution of intensity. Here you can see that some intensity patterns. See, these are some intensity patterns. These are known as intensity patterns. So these intensity patterns explains the location of ions or location of atoms. That is the first point. Second point is that there are two ways of viewing the scattering of X-ray. There are two ways of viewing the scattering of X-ray by a perfect periodic structure of a solid. So there are two treatments. One is Bragg's treatment. We are going to study this treatment, and other one is von der Lewis treatment. Von Lewis treatment. So these two methods are used to explain, to view the scattering pattern of X-rays. So both models yield the same mathematical model. So you can consider either Bragg's treatment or von Lewis treatment. Bragg formulation of X-ray diffraction by a crystal. Here you can see the intensity pattern. So each position, each location provides the different lambda. This is lambda 1, lambda 2, lambda 3. By using the intensity pattern, you can identify the Miller indices for the plan, Miller indices for the crystal structure, and the intensity pattern provides the some kind of location of the atoms or location of the ions, and so many informations we can gather from these intensity patterns. So the above figure shows the intensity variation of scattered X-rays by a crystalline material with a certain incident directions. The significant feature of the graph is that there exist sharply defined peaks for certain sharply defined lambdas at certain incident direction. So the certain direction, you are getting sharp peaks. So this sharp peaks telling that this is the location of the particular atoms or ions. And also not only that, but also you can gain more information from these patterns. So now we will discuss Bragg law or Bragg formula. So in the Bragg law, we are going to consider two assumptions, or we are going to take two important points. The crystals are made up of parallel planes separated by a distance d. So crystals, you know that parallel planes, they are separated by a distance d. The condition for a sharp peak, I mean, we observe that these are sharp peaks, no? These are sharp peaks, sharp peaks, sharp peaks. These are sharp points. These points are known as sharp points. So the condition for a sharp peak in the intensity of the scattered radiations are, what is the condition if you want to get this sharp peak? The first condition is angle of incidence is equal to angle of reflection. Here you can see angle of incident, that is equal to angle of reflection. Here this is, if this is alpha, then this is also alpha. Angle of incident, that is equal to angle of reflection. And the second thing, the reflected beam from successive plan should interfere constructively. There are two types of interference, constructive interference as well as destructive interference. Constructive interference, you have to add the interference pattern. Destructive, you have to subtract from one another. So here you can see the reflected beam from successive plan. These are the refracted beam from successive plans. Successive plans mean the parallel plans. So these reflected beams should interfere constructively. So then only you can observe sharp interference patterns or sharp intensity peaks. So if you want to find the intensity pattern, you have to satisfy these two conditions. Understand? So here you can see this. See, from this diagram, you can see these are the parallel planes, P, Q, R. These are the parallel planes. These are the location of the atoms. Here this is angle of incidence, that is equal to angle of reflection. So angle of incidence is equal to angle of reflection. And see the path difference. What is the path difference is here? You have to consider A, B, D, E. So the path difference is here. This is the path difference. GY plus YH. This is the path AD and BE. So the path difference is the small distance. Here these are same. So GY plus YH. This is the path difference. If this angle is theta, then this is 90 minus theta. Then this is theta. This is theta. This is also theta. So GY is equal to d sine theta. GY is equal to d sine theta. And here also YH is also d sine theta. So the path difference is 2d sine theta. Do you understand this? If you have any doubt, you can ask. 2d sine theta, that is the path difference. The ray A and B will interfere constructively if the path difference is integer times lambda. Do you remember? You already studied this. Path difference, that is equal to n lambda. If you interfere for the constructive interference, the path difference is equal to n lambda. So our path difference is 2d sine theta, that is equal to n lambda. So this condition is an important condition. This condition is known as Bragg's condition, where n is equal 1, 2, 3 up to n. So this is the order of the corresponding reflection. Order of corresponding reflection. So there are three types of methods. There are three types of diffraction methods you can observe. So in order to get a probable diffraction pattern, one of the following methods can be used. First method is powder sample method. In the powder sample method, the lambda is fixed. I mean, we are using the monochromatic light. Monochromatic light means what? Monochromatic light means the light which contains single frequency or single wavelength. Does sodium is the monochromatic light? Does sodium monochromatic light? Anyone can answer. Does sodium monochromatic light?
Yes.
Okay. Does
Yes.
mercury is the monochrome? Does mercury lamp provide monochromatic light? Does mercury provide the monochromatic light? Yes, no. Because which provides the white light. So you can observe the vibgyor from the white light. So that is not monochromatic. That contains a set of light which has more than one wavelength. So that is not monochromatic. So in the powder sample method, we are fixing lambda, we are using the monochromatic light, but we are changing d and theta, that is incident angle. We are changing the incident angle and we are changing d, atomic spacing. The next method is known as Louis method. So the Louis method, here theta is fixed. We are fixing theta and we are changing d and lambda. A single crystal is held stationary. A beam of white radiation, so we are using white radiation, so lambda may varies, is inclined on it at a fixed balancing angle theta. So here we are changing d and lambda. Then other one, rotating crystal method. Here we are rotating the crystal. So theta is varies. Here we are rotating the crystal. So theta is varies, but we are using the monochromatic light. Lambda is fixed. In these three methods, we are going to study only about powder sample method. So this is a powder method or powder sample method, most widely used diffraction method. So here you can see that in this method, this is your monochromatic light source. Monochromatic light source. Here this is your crystal and you are changing the theta. And you can observe the diffraction pattern in the film. This is a circular film. So you can change the diffraction pattern, and if you expand the film, it will become a rectangular shape and you will get this type of fringes. You'll get this type of fringes. Then you expand this film. This is a circular film. After that, you can expand this. When you expand, you will get the rectangular shape film, and there you can find this type of diffraction patterns. The most widely used diffraction method to determine the structure of the crystalline solids. The sample used in the form of fine powder containing a large number of tiny crystallites with random orientation. Why we are using random orientation? Why we are using random orientation? Because here D is varying. D is not equal. D is varying. That's why we are using the random orientation. And also here we are changing. We are observing the patterns with the different angles. With the different angle, we are observing the patterns. So, but lambda is fixed here because we are using the monochromatic light. Mostly we are using the X-rays. So, let me analyze this pattern. In powder method, incident monochromatic radiation strikes finely powdered specimen containing in a thin wall capillary tube. The distribution of crystal orientation will be nearly continuous. The diffracted rays go out of individual crystallites that happen to be oriented with planes, making as the incident angle theta with the beam satisfying the Bragg equation. The diffracted rays leave the specimen along the generators of cone concentric with the origin. The generators make an angle of 2 theta with the direction of origin beam where theta is Bragg angle. So that is what I explained before. So here you can see the cone intercept. This is 2 theta. This is a cone which contains 2 theta. This is 2 theta and also this is 2 theta. See, theta, 2 theta. One cone contains 2 theta. So if you consider this in the circle, in the center of the circle, so you will get this is 2 theta and this is 2 theta, altogether 4 theta. So that is the S. S, and this is the radius R. Intensity pattern. See here, you can see by using these figures. See, 2 theta, 2 theta, 2 theta, 2 theta. So if you consider the circle, 2 theta, 2 theta, 4 theta, that is equal to S over R. Do you understand? This length is S and the radius is R. So different orders will give different theta. The difference comes of diffracted beam will cut the film in circle. So the radius, I already told you that this is S and this is R. Then the angle is 4 theta. So 4 theta, that is equal to S over R. And for the diffraction pattern, so for the Bragg condition, 2D sine theta, that is equal to n lambda. If you take n is equal to 1, then 2D sine theta, that is equal to lambda. So d is equal to lambda over 2 sine theta. So by using these two formula, you can find out A1, A2, A3 for the unit cell. You can find out the DHKL from this, and then you can find out A1, A2, A3 of a particular unit cell. So for a cubic, DHKL, that is A over HK squared plus K squared plus L squared, that is equal to lambda over 2 sine theta. So sine squared theta can be written in this way. So there are some numerical questions for this. I will discuss in the tutorial discussion. So there you can understand how to do the numerical questions in the powder sample method. So I will share the notes to you. However, I have to conduct the continuous assessment. I think you didn't do any continuous assessments for this. I am waiting to do it physically. Otherwise, I have to conduct via online board. However, prepare for everything. If you have time, please study well. And if you have any questions regarding this, please send me a message to me. I will explain in the lecture time. Okay, so I'm going to wind up the lecture today. Thank you so much for hearing this.